Hello everyone. Welcome to episode 6 in the op-amp tutorial series, the Inverting and Non-Inverting Summers. If you haven't had a chance to see the previous episodes, you can check them out on the channel. In the previous episode, we did lab demonstrations for the resistive non-inverting amplifier, the resistive inverting amplifier, the integrator circuit, and the differentiator circuit. So we've done a few circuits with single input and single output. But what if we want to combine multiple signals together to generate an output? Maybe we want a control signal to be determined by 3 separate sensor signals. Perhaps we want to implement a PID loop in the analog domain. We can just use a normal inverting amplifier for the proportional, an integrator for the integral, and a differentiator for the derivative. But once we have all these signals, we need to add them all together. How would we do that? The answer is by using a summing circuit. Today we will be introducing the summer circuit, discussing and deriving the transfer functions of the inverting and non-inverting summer circuits, as well as discussing the advantages and disadvantages of each summer type. Summer circuits are circuits that add 2 or more voltages together to create a single output proportional to the input voltages. They are used to synthesize complicated waveforms by adding together multiple signal sources. They are also used to combine multiple control signals together to drive a control system, such as the analog PID controller we mentioned earlier. They can also be used to add a DC offset to a signal or multiple offsets from multiple sources. Another common application is when the main signal contains undesirable components. They can be subtracted from the main signal by generating an auxiliary signal made up of these undesired signals, then adding an inverted version of this auxiliary signal to the main signal using a summer circuit. These are just a few applications. There are many more. It is ultimately a vital circuit for any system that requires generating a signal from the sum of 2 or more other signals in the analog domain. Here we have the inverting summer. To simplify things, we're starting with a 3-input circuit. Then later we will introduce the general n-input circuit. Here we have the 3 input voltages, V1, V2, and V3, each connected through a separate resistor to the op-amp's inverting input. There is also a feedback resistor, RFB, connected between the output and VOP-. This configuration is a slightly modified form of the inverting amplifier, with multiple input voltages and resistors connected to the inverting input, rather than a single input voltage and resistor. Note that here we have connected the non-inverting input to ground for simplicity, as we have done with the other inverting circuits thus far. Here we've drawn the currents I1, I2, and I3, which go through each input resistor, and IFB, which goes through RFB. We've also drawn IOP plus and IOP-, which are still equal to 0 per the ideal op-amp tenets. Now to compute Vout, as with previous inverting amplifier circuits, we have to find an expression for IFB in terms of known parameters. So looking at our currents, we see that I1, I2, and I3 must combine to equal IFB by Kirchhoff's current law, since IOP- is 0. Now, although this circuit might look difficult to analyze, it's actually quite straightforward. Since we have the virtual ground here at VOP-, we can actually split off all the input voltages and their respective input resistors to individual resistances, each connected on one side to ground, as shown. This results in simple equations for the 3 input currents. Now, substituting in the expressions for those currents yields an equation for IFB in terms of known parameters, the input voltages and resistor values. Similar to what was done for the simple inverting amplifier, multiplying that current by RFB and subtracting that value from our virtual ground yields an equation for the output voltage Vout in terms of resistor values and input voltages. This circuit can be easily extended to n inputs simply by adding more voltage and resistor connections like the first 3 values. This is the resulting general equation for Vout with n inputs. So we see that each input voltage is weighted by a factor of RFB over that signal's respective input resistor in the final output, and all the weighted values are added together. This makes it very simple to do a weighted sum by adjusting the resistance values to give different weights to each input voltage. One notable downside of this circuit is the same downside as we've noted for all inverting amplifier circuits, namely that the input impedance is not high, but is equal to the input resistor. Furthermore, to change the relative weights of each input, one must have different input impedances for each input, which may be non-ideal for some unbuffered sources, especially if the difference in weight required between two of the signals needs to be significant, like a factor of 10 or 100, which leads to impractically high or low resistances. There are workarounds for such a situation by using resistive dividers or additional amplification, but the cost and effects of these mitigations in the larger circuit must be considered to determine the optimal solution for the application. Here we move on to the non-inverting summer. The non-inverting summer, as you might imagine, uses a modified form of the non-inverting amplifier configuration. Apart from that aspect, it looks schematically very similar to the inverting summer. We will derive the equation for the 3-input non-inverting summer and discuss what a summer with an arbitrary number of inputs looks like afterwards. Each of these 3 voltages on the resistors will produce a current. I've noted IOP plus here as a 4th current. However, we recall that the current into the op-amps is 0. Therefore, this circuit is fundamentally different from the inverting summer, as we cannot rely on the virtual ground node to separate out the 3 input currents. We can actually see that the input stage of this circuit, with the 3 resistors, can be separated from the amplifier aspect, creating 2 separate circuits to solve. First, let's focus on the input stage. We'll denote the voltage that goes into the non-inverting amplifier input, VA. The goal here now is to find VA as an expression of these known resistors and these input voltages. So first we can create equations for all 3 currents using Ohm's law and the still unknown VA. Using Kirchhoff's current law, we know that all 3 of these currents cancel each other out since there's no current out of VA into the op-amp. Substituting in the expressions for the currents in this KCL equation, and then gathering all the VA terms on one side, and simplifying using some tedious algebraic manipulation, we get the equation for VA, which looks a little ugly. Now let's take this equation and combine it with the non-inverting amplifier portion of the circuit to see the result. All we need to do here is recall the non-inverting amplifier's transfer function derived in episode 3 and set VA as the input voltage, meaning that all we need to do is multiply the expression for VA by the non-inverting gain, which yields this equation. Note that each voltage has a different weight that can be controlled by the resistances in the circuit, as well as a global weight provided by the non-inverting amplifier gain. Regarding the general formula for N resistors, you can see the pattern in the equation here, where in the numerator, each voltage input is multiplied by all the input resistors except for its own series resistor. Then all those terms are added together, and the denominator looks the same as the numerator, except with all the voltage values set to 1. For completeness, here's the formal equation for the general solution. Yeah, it's not pretty, but it's the same as the intuitive answer. And if using the general solution is too much of a headache, just resolve the circuit for whatever number of inputs you need. It's not too difficult, especially since very few applications will have n be a large number. One additional derivation needs to be done, the input impedance of the non-inverting summer, as it is relevant to the discussion of the pros and cons between the 2 summer types. To do this, we examine each of the input signals' individual impedance independent of changes in the other input voltages. We know we can do this because we assume this is a linear time invariant system, and so we can use the principle of superposition to separate the 3 signals. So all the input signals, apart from the signal we are evaluating the impedance of, are set to 0 volts. Now we just have some simple circuits, so let's just rearrange them so they look more normal. And now all we need to do is apply our series and parallel resistor formulas to come up with the input impedances for each input. So here we see that the input impedance for the non-inverting summer is higher than the inverting summer for each input by the parallel combination of the other 2 input resistors. For the general form, it's just the resistor corresponding to the input signal, Rk, in series with the parallel combination of the remaining input resistors. Note that this does not mean that the other voltages cannot affect the current from the signal Vk. It just means that when you keep the other signals at a fixed value and then change Vk only, then the input current will change based on this input impedance. So the input impedance of the non-inverting summer isn't actually that much higher than the inverting summer, though this can still be significant depending upon the ratio of the weights of the inputs, especially if that ratio is very large. Now let's take a look at the pros and cons between these two summers. The main advantages to the inverting summer are: it's simple to set and calculate the different weights for the inputs. Changing the weight of one signal doesn't change the weights of the other input signals. The input current for a given voltage signal input only depends on the input resistor for that signal and the signal's voltage with respect to the virtual ground. It does not change if one of the other input signals changes. It's simple to introduce a global offset into the non-inverting input that also allows control over the voltage of the virtual ground. We'll discuss the implications of putting a non-zero voltage on the non-inverting input in the inverting amplifier configuration in a later video. The common mode input voltage for the inverting op-amp is equal to the virtual ground. This both eliminates non-idealities stemming from changing common mode input voltages, as well as allows for the input voltages to be almost anything. So long as the application does not cause the op-amp to rail, the input voltages can exceed either power rail if desired, as the op-amp will never see those voltages. The main disadvantages of the inverting summer are: the required application gain drives the maximum input resistance. Having high resistor values reduces the impact of the summer circuit on the input circuits and reduces the power consumed by the op-amp circuit. However, there is a point at which increasing the resistance causes some non-idealities to become significant problems, mainly noise, finite op-amp input currents, and the effect of parasitic capacitance. Since the gain of the circuit is dependent upon the ratio of input resistances to the feedback resistor, if you increase the input resistors to a high value and need a high gain, then the feedback resistor also has to be very high. The non-inverting summer does not have this problem. This summer is inverting, which may require adding another op-amp to invert the result, which could be a small issue or a larger issue depending upon the application. It has a somewhat lower input impedance than the non-inverting summer because the input impedance for each input voltage is equal to just the input resistor. The main advantages of the non-inverting summer are: it has a generally higher input impedance, the gain of the summer is decoupled from the summing node resistances, as the summing resistances apply weights to the input signals by their relative sizes, then the global gain after that is determined solely by the gain-setting resistors RG1 and RG2. This means that maximum valued resistors can be used on the input side, and a large gain can still be applied because RG1 and RG2 can be sized independently to avoid any unpleasant non-idealities. Note that there are still practical limits to the size of the input side resistors, but these are not tied to the gain in the same way as with the inverting summer. It does not invert, which may allow a signal chain to have one fewer op-amp, making it smaller, cheaper, and more efficient. The main disadvantages of the non-inverting summer are: modifying any of the input resistors will change the effective gain experienced by the other input voltages. This makes adjusting the weights a little more complicated than with the inverting summer. Unlike with the inverting summer, the input current from one input is affected by the other input voltages, including the direction of that input current. As a result, this can cause problems if one of the input voltages is only capable of providing current in one direction, sourcing, for example, and the other input voltages become a very high voltage, causing the voltage at VA to be greater than the input voltage sourcing signal, causing the signal to not produce the proper output voltage and corrupting the output signal. Also, unlike with the inverting summer, the common mode voltage of the non-inverting summer, as with other non-inverting circuits, moves around based on the input voltage signals. This introduces non-idealities and significantly restricts the allowable voltages at the inputs, and in a somewhat complicated way due to the way the voltages interact with one another to produce VA. As a final note, in general, the inverting summer is the preferred kind of summer due to its simplicity and static common mode voltage, and you only use the non-inverting summer if the advantages significantly outweigh the disadvantages for your particular application. That concludes this episode. In this episode, we talked about summing circuits, introduced and derived the output voltage equations of the inverting summer and non-inverting summer, and discussed the relative advantages and disadvantages between the two summers. In the next episode, we will be doing a lab demo of the two summers. Thank you for watching the video. If you enjoyed it, please like, share, and subscribe. See you next time.